Hi everyone, welcome to this video on sample size planning. My name is Keith Lose and I'm an associate professor in physical therapy and neurology at Washington University in St. Louis. This video is meant to be kind of an asynchronous complement to an in-person workshop that's happening at the North American Society for the Psychology of Sport and Physical Activity, or NASPSPA, that's being put on by a number of faculty. I'm helping kind of with this event remotely and designing some of this asynchronous material. After you've gone through the workshop, for those of you who are there, we hope this will be a useful reference for you moving forward. For those of you who maybe are just picking up on this video otherwise, hopefully it's still helpful and informative with respect to sample size planning. To give you a sense of where we're going to go, I'm going to provide two videos that give us kind of a high-level introduction to what is statistical power and how we can build some of our statistical intuitions. Then I'm also going to have some videos that walk through simulations using R code in order to simulate different study designs and statistical tests that you might do so that you can actually get sample size estimates for some more complicated situations that are difficult to build like standardized effect sizes for. So that's where we're going over a course of about 5 videos. There's also going to be a GitHub repository that I'll link to in the video description that has all of the code and all of the PowerPoint slides. If you find any of these things useful, you're welcome to download those. But let's get started with talking about what is statistical power. So hopefully you're a little bit familiar with statistical power already and some different types of statistical analyses. But to refresh your memory, or maybe to give you a really firm definition, statistical power is the probability of obtaining a statistically significant result, assuming that some real effect is this, or exists. What we can often think about that is kind of a 2x2 table where we're going to conduct some kind of hypothesis test and we'll get a p-value, compare that to our alpha level, right? And we might then reject the hypothesis or the null hypothesis, or we might fail to reject the null hypothesis. And of course, that decision then has to get mapped onto reality where the null hypothesis might be true or the null hypothesis might be false, right? And ideally, we want to be in kind of these two areas of the diagonal where we're getting true positive results, we're rejecting the null hypothesis when it is false, or we're getting true negative results, which is to say we're failing to reject the null hypothesis when it is in fact true. And we're trying to avoid two different types of errors, right? Type 1 errors are false positives, would be when we reject the null hypothesis, but it's actually true. And type 2 errors or false negatives would be when we fail to reject the null hypothesis, but the null is actually false, so we should have rejected it. So we're going to talk a little bit about both components to this kind of framework, where first we have to maybe refresh what a null hypothesis significance test is and how we use it to make decisions. And then we can better understand statistical power, right? And what it actually means to have a true positive in this framework. But one of the key things I'll point out is that we don't actually know most of the time, right, if the null hypothesis is true or false. Because if we did, we wouldn't have to do a statistical test to make a decision. So we're going to make some assumptions when it comes to calculating statistical power. In the same way that when we do a null hypothesis test, we assume that the null is true. When we calculate statistical power, we have to assume that some alternative hypothesis is true and say, well, okay, what if reality looked like this? What would our statistical power be? So we're going to talk through that in much more detail, but I just wanted to lay that out there as kind of our starting point for this framework. We have to conduct a hypothesis test, and we're going to be balancing the cost of these two different types of errors. Now, a detailed discussion of statistical power is totally beyond our scope. You know, that's a class in and of itself. And this video is already going to be probably longer than it should be. But there are some important considerations that I think you should remember if you get nothing else out of this video. First, all studies should present some justification for their sample size or consideration for statistical power. That doesn't mean that they have to have very good power for their primary statistical tests, because there might be some logistic constraints on the sample size, right? But if the study is not well powered for those primary results, it should say that, and it should explain why, right? So there should be some explanation of why the authors collected the data that they did and how that relates to the statistical power of their tests. Furthermore, power depends on very specific dependent variables and statistical tests. So there is no single power calculation that covers the entire study, right? People might say, ooh, that was a well-powered trial, but that's not actually correct. Statistical power really only applies to a very specific type of test. Is it a between subjects t-test or a within subjects t-test? And it depends on the outcome, because it's going to be based on how strong the effect is relative to the variation. And those two things depend on what you're measuring. Right? So this is part of why designating a primary outcome is so important, because statistical power is very contextual and you can only really be powered for specific tests. Now, if you have multiple tests, you could build your sample size around the smallest one, right, to make sure you're powered for all of them. But it's important to remember that power is specific. It doesn't blanketly cover an entire study. And again, a power calculation is only as good as its assumptions. If I assume that the true effect is enormous, my power calculation might tell me I only need to study 10 people. But was that a good assumption to begin with? Or was I being overly optimistic? Now, again, statistical power is the probability of obtaining a statistically significant result, assuming that an effect actually exists, right? That some alternative hypothesis is in fact correct, and we're going to detect it. So we can do that with many different types of statistics and across many different study designs, but the same factors are going to affect statistical power. And those are going to be the size of the effect, the size of our sample, the variance in the data, or the variability, right, of the data, and then kind of the tipping point will be the math and the balancing of the type 1 and the type 2 errors. So for instance, right, if we want to get a statistically significant result, because again, if we're assuming that the null is wrong and that the some alternative hypothesis is correct, we would want to get a big t-value in a t-test, because that's more likely to be statistically significant. And these factors, right, will drive that t-value up. So if we have a really big difference between our groups, or if we have a really big sample, that's going to make the t-value we observe bigger, making it more likely that we will correctly reject the null hypothesis if it's wrong. Similarly, variance works in the opposite direction, right? It makes us less certain, and it's going to drive this t-value down. So if we have a very large sample variance, the t-value we observe is going to get smaller, making it less likely to be statistically significant, and therefore going to have a negative effect on our statistical power. So all of these parameters are at play when we consider the statistical power of a study. Most of the time we talk about sample size, and we say, okay, can you make the sample bigger? What is the n that you need in order to achieve 80% statistical power or 90% statistical power? But you can actually adjust any of these parameters. For instance, is there something you can do to make the effect bigger? Can I actually give my intervention in a much stronger or more powerful way? Because if I can increase the size of the effect, that can actually often be a lot more cost effective than recruiting 100 more people into my study. Similarly, can I reduce the variance? Maybe I can homogenize my sample by using tighter inclusion or exclusion criteria, or strategically use some covariates to explain residual error. And if I can do that, right now the background variance is getting smaller, proportionally the effect size looks bigger, and I'll be able to increase my statistical power while keeping the sample size the same. Similarly, right, we can also consider where this tipping point is and what levels of alpha or beta are actually desirable. Typically, we set alpha to 0.05 and we set beta to 0.2, which is the same as having 80% statistical power, because power is 1 minus beta, right? But we could actually set those to anything that we want. We just have to have a really good justification for why we're setting them to where we're setting them, right? We set alpha at 0.05 and beta at 0.2, usually because we think that false positives are riskier than false negatives. So we'll keep that alpha level lower in order to reduce the type 1 error rate and try to prevent seeing false positives when the null is in fact true. But that's not always the case, and it's important to remember that these things are going to trade off. So the more conservative I'm going to be and avoid a false positive, that's going to open the door for more false negatives. And we'll show you a little bit more about that in a second, but it's important to remember that those two things do trade off. Additionally, there's not just one approach to statistical power given these different constructs that we can measure. So most of the time, people, when they're talking about statistical power, are talking about an a priori power calculation, which is we're going to assume some specific alternative hypothesis. So we assume some true effect and some true variance, And then oftentimes we'll calculate a standardized effect size. So in this case, like a Cohen's d of 0.5, if our true effect was half as big as the true variance. Then in an a priori power analysis, we're going to calculate the number of people that we need in order to achieve 80% statistical power for a given level of alpha. So with an a priori power, you're solving all of this to find the n that you need when power is 80% or 90%. A complementary way of doing this, though, is to look at sensitivity, or what you might call achieved power. So if you say we're only able to recruit 30 people because maybe it's a very small population or it's a very cost-prohibitive intervention, you can then say, well, what kind of effects did you have the power to detect? So with a sensitivity analysis, you're fixing n and you're solving for the ratio of kind of the true effect to the true variance. Given the sample size, what kind or size of effect did you have the statistical power to detect, assuming, you know, a certain level of power and a certain level of alpha. The final one that you will sometimes see is what's known as post hoc power, and I would encourage you never to use post hoc power because it is a bad statistic. In post hoc power, what you do is you assume that the true effect is equal to the effect that you observed in your study, and then you calculate the power you had to detect that effect. And this just becomes a self-fulfilling prophecy based on your null hypothesis significance test. If you had a significant result, post hoc power will tell you that you had the power to detect it. If you have a non-significant result, post hoc power will say you did not have the power to detect it. So it's a pretty meaningless statistic. And the thing that I would tell you, right, again, is we are going to make assumptions. When we're making a priori power, we have to make some assumption about how big we think the true effect really is. With post hoc power, what we're doing is assuming the true effect exactly equals what we saw in our sample. And that's a pretty silly assumption, because what are the odds that we happen to observe exactly the true effect? They're pretty small. Chances are we maybe observe something in the ballpark of the true effect, depending on how big our sample is, right? But it's almost never going to equal exactly the true effect. So the starting idea of post hoc power is just not great, and I would encourage you never to use it. Okay, so to dig a little deeper into power, first we're going to start with a null hypothesis test, because again, power is the probability of obtaining a statistically significant result, assuming that there is some real effect. So we have to understand what the null hypothesis test is in order to understand what it means to get a statistically significant result. So again, our null hypothesis is the hypothesis to be nullified, and we're going to make a set of assumptions, which we call our null hypothesis. And if our data strongly conflict with those assumptions, then we would reject the null hypothesis and say these data were unlikely to arise if the null was true. So often what this looks like, right, is we're going to make some assumption of no effect. So the null hypothesis would be that the true population mean for the treatment group is equal to the true population mean for the control group, or equivalently, you could write this, that the difference between those two groups is 0. There's no difference in the population. And here are some data that I've simulated where that is true. So these are samples, right, where the true mean difference is 0. But these are relatively small samples, and you can see that they're bouncing around a lot. And so we get a pretty wide range in the distribution of sample means. Some sample mean differences are right around 0, and that's great. But sometimes the sample mean difference is as large as 2. Sometimes it's as large as, almost negative 3. So we're getting quite a bit of variability due to sampling, right, when we go back and resample from this population. And if you did this a theoretically infinite number of times, eventually you're going to end up with a normal distribution, given the central limit theorem. And so assuming that the true mean difference is 0, we're going to end up with a normal distribution that is centered on 0 and has a standard deviation based on the size of the sample and the variance in the data, right? Because this would spread out based on the standard error of the mean. So this is basically our assumption. When we say we're doing a null hypothesis test, this is the null hypothesis, this red distribution. This is the sampling distribution we would expect for samples of a given size. So let's say that we observed a mean difference of 0.5. Is that statistically interesting under the null hypothesis? No, under the null hypothesis, a mean difference of 0.5 is well within the bounds of what we would expect due to sampling variability, right? It's super common to get a mean difference of 0.5, even when there truly is no mean difference. So this isn't really statistically surprising or interesting. What if we observed a mean difference, though, of about 3, right? And our mean difference was all the way over here. Well, yes, if the null hypothesis were true, this is very unlikely to arise, and therefore we would probably reject the null hypothesis as an explanation for these data. And we'd say, you know what, I think there's something else going on because we were unlikely to have observed a mean difference this large if the null hypothesis were true. So what about a mean difference of 1.5, something a little more moderate? And now the answer is, well, maybe. This seems kind of statistically interesting, right? It's less likely than a 0.5, but it's more likely than a mean difference of 3. So what do we do with this 1.5? And we could kind of debate, you know, okay, well, maybe to some people this seems more interesting and here's the reason why. To other people this seems less interesting and here's the reason why. But one way of cleanly resolving the ambiguity around these boundary cases is type 1 error control. We can set the alpha level and say, all right, it has to be in the extreme tails. And if it is beyond that point, we will say it is statistically significant. And if it is not beyond that point, we will say it is not statistically significant. So in practice, we often set alpha to 0.05, which means we're going to isolate the middle 95% of the distribution from the tails, right? So we're going to put 2.5% in this tail of the null distribution and 2.5% in this tail of the null distribution. And now, anytime we get a result that's exceeding that percentile, we would declare that statistically significant, and that is interesting under the null, and we would decide to reject the null, right? So when the null hypothesis is true, the advantage of doing this is we're only going to make a mistake 5% of the time, right? So if the null hypothesis is true, 95% of mean differences we observe will be here. Sometimes we'll get one that's weirdly small or we'll get one that's weirdly big, but that's only going to happen 5% of the time when the null is true. So we could be more conservative about that, right? If, oh, well, I don't want to make an error 5% of the time, that seems bad. You might want to set your alpha level even higher. So we could set an alpha level of 0.01, which means we're now isolating 9.9% of this distribution in the middle. And we have 0.05% right over here. And we have 0.05% over here. So now this result that used to be statistically significant, right, no longer is. We're being more cautious. So we're going to cut down on the number of false positives by getting a tighter and tighter alpha level, which means we're going to call fewer and fewer things statistically significant. Keep that in mind, though, because in the next few slides, we're going to look at this also through the lens of statistical power. And if we're being more conservative here and avoiding false positives, that means we're going to be accepting more and more false negatives. Basically, we are going to, if you set alpha lower, you have a higher standard of evidence for what you consider statistically interesting, and that means you're going to call fewer and fewer effects statistically significant, which means you'll miss some real findings because you're being more cautious and you're being more conservative. To see that a little more clearly, let's look at a few sampling distributions, and we'll start with the sampling distribution when the null is true. So this is almost identical to what we looked at before. Now I've specified that this is actually an n per group of 10 individuals. But again, there's no true difference between the two populations that I'm sampling from. And then each of these dots is an experiment where I take 10 people from the treatment group, 10 people from the control group, calculate the difference between their two means. And you can see how those dots build into a normal distribution over here. And I'm color coding these dots now based on whether or not they are statistically significant, right? So if given the actual mean difference and the standard error that we calculate in that given experiment, do we get a p-value less than 0.05? And the complementary plot over here is the distribution of p-values. So you can see as these things kind of fill up, we get the mean difference and the effect size over here, whereas we get the p-value over here. And if you let those run, again, like a very large number to a theoretically infinite number of times, we're going to end up with a nice normal distribution of mean differences over here. But you'll see that sometimes we get statistically significant results. Specifically, right, if we set alpha to 0.05, it's going to happen 5% of the time. And you can see that really nicely in the distribution of p-values. When the null hypothesis is true, the distribution of p-values is approximately uniform, and therefore you're going to get 5% of them that are less than 0.05. Right? So when the null is true, we can avoid false positives by setting that type 1 error rate. They're still going to happen, right? But we can greatly cut down on the number of times that they do happen by being conservative with that alpha level. Now, what about when the alternative, or well, I should say an alternative hypothesis is true? Because when we're calculating power, we have to assume a specific alternative hypothesis, right? We can't simply say, well, what if the difference is not 0? We have to assume that the difference is a certain amount. So in this case, we're taking samples of the same size, so it's 10 people per group. I'm randomly sampling from the treatment group and from the control group, but the true difference between these groups is 0.5. My treatment group has a mean that is 0.5 points higher than my control group. And now you can see I get this nice normal distribution. Again, if I let this kind of build up, I get one experiment, calculate the mean difference, take another experiment, calculate the mean difference. And again, with each one, I'm going to get a p-value and decide if it is statistically significant or not. And now you can see a shift in the distribution of our effects and a shift in the distribution of our p-values. In the effect size distribution, right, now rather than being centered on 0, this is centered on 0.05, or sorry, on 0.5, because again, I've controlled what the truth is here. And now I'm saying the null is false. Actually, it's 0.5 is the truth. And now you can see then our normal distribution is centered on 0.5. It still spreads out to the same degree because, again, there's the sampling variability and the size of the groups are the same. So we've really just kind of shifted this distribution slightly to the right relative to the previous simulations. And you can also see, again, that extreme events still occur. So we're going to get some extremely low values. Even though the null is false, we're not going to call those statistically significant. And we're going to get some quite high values, right? So these are statistically significant, but they're actually really bad estimates of the true effect. So the true effect is 0.5. And you can see that in a sample, when I get a 0.5, it's almost never statistically significant. In fact, in this case, I think it never is statistically significant right at 0.5. And in my small samples, I actually have to get quite a large difference before I call it statistically significant. So this is sometimes referred to as the winner's curse, because when I have a study with very low statistical power, even though I'm getting a statistically significant result, technically I'm getting the right answer. I've rejected the null hypothesis when it is false. My estimate is bad, and I'm overestimating what the real effect actually is. So that's definitely going to be a concern. But a bigger concern just from a testing perspective is I'm only correctly rejecting the null 19% of the time now. Notice that when the alternative hypothesis is true, our distribution of p-values is shifted, right? So now there's a greater mass of very small p-values, and we've got this kind of right skew in the tail. But we're not doing really well. So our alpha level is still at 0.05, and only 19% of all of our p-values are less than 0.05. So that's 19% statistical power, right? 19% of the time, we're obtaining a statistically significant result when the null hypothesis is not true. It's false. But that means 81% of the time, we're making a false negative, right? We should be saying, hey, we should reject the null. The null is not true. But 81% of the time, we fail to do that, and it's a false negative. So this is kind of a terrible situation. What can we do to make it better? And one thing that we can do to improve our statistical power is to increase our sample size. So let's do this now with, rather than an n per group equal to 10, an n per group equal to 64. So now, with an n of 64, you can see that my distribution of mean differences is still centered on 0.5, right? Kind of following the central limit theorem. The sampling distribution is going to be centered on the true mean difference. But it's much tighter in its spread. With 64 people per group, that standard error goes way down, and I get much less variability from trial to trial. And if we look at sort of our statistically significant results here, you can see that when I actually get a 0.5, I'm calling that statistically significant. So not only am I making the right decision most of the time and correctly rejecting the null hypothesis, but I'm also getting much better estimates and much more usable estimates when I do make that decision to reject the null. So in an absolute sense, we've cut down on some of those extreme observations, and all of our effect sizes are much better estimates of the true value. We're also now correctly rejecting the null hypothesis 80% of the time, which means with n per group of 64, we have 80% statistical power to detect a mean difference of 0.5 in this case. So that's great, right? Well, okay, we're correctly rejecting the null 80% of the time. We've really cut down on the variance, so our estimates are going to be much more informative and more accurate. But we had to recruit 128 subjects in order to do that. So that is not great, right? For most intents and purposes, 128 is probably a lot. That's a significant investment in a randomized controlled trial. So what can we do to maybe make this situation better? Well, part of the harsh reality is that sometimes we might just have to recruit 128 subjects. We might actually have to recruit quite a bit more than that. And that's one of the things that we're going to talk about. But there are things you can do to try and improve the size of the effect or cut down on the variance in order to improve statistical power. But at the end of the day, sometimes you're going to have to recruit really large numbers if you actually want to have confidence in the decisions that you're making. So to recap, statistical power is the probability of obtaining a statistically significant result, assuming that a particular true effect exists. And again, we have to make an assumption about what that alternative hypothesis is, and we need to make sure that that assumption is reasonable. Otherwise, our power calculation isn't going to be very useful. Sample size, effect size, and variance all interact to affect statistical power. So we're going to focus a lot on how many people we need in order to achieve a high level of statistical power. But keep in mind that sample size is only one of several factors that affect statistical power. And if it's reasonable to increase your effect or to decrease the variance, those things can often be more cost effective than increasing the sample size. The problem is these things are not always under our control, whereas the sample size is much more often under our control. And finally, statistical power is highly contextual. It's specific to a particular hypothesis test and outcome measure. So no one power calculation covers a whole scientific study.